Cool. All right, hello and welcome to our Winter 24 Robotics 530 final project presentation. We're Team 4. We will be presenting about Apriltag landmark localization with the right invariant extended Kalman filter on a low-cost educational robot. So a quick overview for today. We'll go through motivation for our problem, methods we used, experiments we conducted, the results that we got from that experimentation, a discussion of those results, and then future considerations. So getting into motivation, one thing we see with cost-conscious robots, that in a dynamic environment, they may struggle to achieve a robust SLAM performance due to limited computational resources and a lot of sensors for robust SLAM being expensive. And by using these cheaper sensors, such as IM user encoders, these robots are very prone to state estimation drift or odometry drift, as seen in the image in the right, where we actually drive the blue path. The robot estimates that it has driven the dotted green path, leading to drift from the start to finish locations. Another thing that we noticed with this is that with the landmark localization, an easy and cheap way to achieve this is with Apriltags, which are a fiduciary marker system invented at the University of Michigan, which provide a cost-effective landmark, easily detectable with the camera and Python and OpenCV. And all of this can be tested on a real-world implementation of a cheap robot called an MBot that we have here at the University of Michigan. So moving quickly into the methods. The general overview of our system is that on our robot, we have our encoders to provide an estimation of our velocity and our odometry, and we have a camera which can detect the Apriltags in the robot frame. The encoder data will be sent into a right invariant extended Kalman filter for the prediction step, and whenever we have an Apriltag detection available, that will go into the correction step of the Kalman filter, outputting a filtered robot pose, which you'll later see is an improvement upon the odometry. So for the Apriltag detections, the way that this works is we have a camera mounted on the MBot, and by using OpenCV and Python with an open source Apriltag library, we can easily provide the X and Y coordinates of the Apriltag in the MBot frame. And since the Apriltag size is known, if we have a calibrated camera on the robot, this is done very easily, basically right out of the box, and takes very little setup and was very easy to implement. So moving on, we'll talk with Camille to learn more about the right invariant extended Kalman filter.
Yeah, so the reason that we chose the right invariant extended Kalman filter is because of yeah, it provides better handling of nonlinear dynamics over a traditional extended Kalman filtering because it operates within the Lie group. And the reason that we chose the right invariant extended Kalman filter is because our measurements are in the robot frame, which makes it really easy to use this right invariant Kalman filter. And the right invariant Kalman filter just propagates the mean and covariance through a motion model and then updates those with a correction step. So the robot motion model, our state is in SE2. So we have an X position, Y position, and theta. And this gets updated through our two inputs, which is our linear velocity V and rotational velocity omega. And then over time, this will get updated and our covariance will grow as well. And you can see in the image on the right, our robot is a non-holonomic differential drive robot, and it can move forward or turn. And so looking at diving into our actual algorithm, some of the things that we're given are F, our dynamics model, which I just showed previously, our X initial, sigma initial, which is our initial state and initial covariance, W, the motion noise covariance, and then V, the measurement noise covariance. So we initialize our X and sigma, and then in a while loop, while our task is not complete, we get our control inputs, V and omega, from the encoders, and then we update X and sigma through our prediction step. So if you look at algorithm 2, we'll send X, Y, theta, V, and omega through our dynamics and get a new estimated X, Y, and theta. And then we'll put that into our SE2 pose, calculate a twist vector between the previous pose and the predicted pose, and then propagate that through our state and our covariance. And then if we get a Apriltag location, then we'll get the measurement 1 and measurement 2, and ID 1 and ID 2 for each April tag. And the reason that we're using 2 April tags per detection is to get a fully observable Gramian matrix that's full rank. And that allows our pose to be fully observable. And then with our correction step, we'll propagate that through and then update our X and sigma. And then I'll hand it off to Max for the experiments.
So going into the experiments, so now that we have, the kind of framework of how we want to apply our right invariant extended Kalman filter, we need to gather some data. And to do that on a real life MBOT, we decided to run some experiments. So in our case, we created our own data set using this MBOT, and we equipped it with the camera, as described back in when Cameron was talking about the intro. And then from there, we commanded this MBOT to drive in a square. Using keyboard commands commanding velocity and angular velocity, and we would put April tag pairs around like each corner of the square. So as the MBOT is driving along this path, it can detect the April tags using the camera and localize and correct its measurements that way. And all of this data is stored in an LCM log file, which then can be converted into a CSV and then fed into the Python script where the filters run offline to get the results. Here's like a short video of the robot's perspective and how it detects the April tags as it's driving through the square. This is obviously sped up in time, but you can see that as it drives around along each edge, it can detect the April tag and then display its coordinates and ID in the top left. So that is kind of how we use it to gather our data, and then from there export that into a CSV. So going to the results based off of the data that we collected, and running this animation on the top right, we can see that we have our ground truth, which is pretty much the square that we talked about. And then we have these landmark locations that are, known in its absolute position. And then from there, we track the odometry of the robot and then the state using the updated extended Kalman filter. And we can see that as the robot drives around the square, the odometry tends to, drift over time as it is not, very accurate. And the state estimate or the state result of the Kalman filter results in a pretty good tracking of the square as the robot is driving around. And this filter position reduced the root mean square error by over 78% from an error of 0.16 using odometry to 0.04 meters. And then the parameters we used to kind of tune this extended Kalman filter had a resultant motion noise standard deviation of 0.03 meters per second in linear velocity and 0.01 radians per second in angular velocity, with a measurement noise standard deviation of 0.1 meters. And this, these values kind of make sense based off of some of the measurements we took and compared it to. So for the most part, that we tested that this Kalman filter works pretty well given the results of our data. Going into the discussion and the conclusion, so pretty much we concluded that this, we can effectively improve our robot's pose estimation over time with the use of landmark localization, resulting in a greater than 75% error improvement. And this is also, computationally efficient method of, correcting this odometry, as it only involves, using matrices. So this could theoretically be corrected, done online on the robot live. And then another thing to note is that, as we're collecting this data, the experiment itself is rather time consuming because, you have to determine what kind of a setup we want to use. And then how do we convert all of that data that we collected on board into, a log file and then CSV, and then setting up the April tags in a consistent manner also proved to be time consuming, as you have to determine the absolute, positions of these April tags and measure them out before you set them in any arbitrary location. So now I'll throw it over to Camille to talk about, future considerations and work to do afterwards.
Yeah, so some of our future considerations to extend this project would be to actually have it working live on the MBOT. So creating an LCM node that would subscribe to the robot pose and then update that. There would be like a Kalman filter node that would publish a new position that could be subscribed to. And then another idea that we had was improving our motion model. So in this experiment, we did not use any of the IMU data, but we can use that as well as part of our motion model. And then since we're already recording video or getting video data to detect the April tags, we can also use the camera as our motion model for visual odometry. Another idea that we had was to simplify the setup. So this idea would involve having one camera that would be a bird's eye view of the map, and then having one April tag per robot. That would eliminate the need for multiple landmarks and just have one sensor for multiple robots, and each robot would have a unique April tag on it. And then the other idea would be to extend this to 3D, for example, a drone, and use this in SE3. And thank you all for a great semester.